Hello, my name is Tommy and welcome to my Pandas tutorial. Pandas is a Python library for manipulating data. It's an old, mature library compared to a lot of other open source libraries. And as you can see on this graph, it's rising in popularity and has been for many years. Other technologies might be on the decline. This tutorial is me running through a notebook, and I'm going to be talking while doing so. The table of contents for this tutorial is shown here. I'm going to talk about how to install Python packages and how to import them. So it's quite a beginner-friendly tutorial, but I kind of hope that you've played around with Python for a little bit. If not, this might be a bit confusing to you. I'm going to talk about how to import data from the web, from CSV files, how to create data frames from scratch. Then we're going to talk about summarizing data, and finally selecting and computing new columns. What's different with respect to other tutorials? Because there are a lot of other good tutorials. The difference is that in this tutorial I hope to be really concise. In the description of the video there's a table of contents where you can skip to whatever you're interested in. I'm going to talk quite quickly, go through things quite quickly, and you can pause if you wonder about something. So compared to a lot of other Pandas tutorials where sometimes you spend 3 hours and you just scratch the surface, I really hope to have a faster pace than some of the other tutorials, which is the kind of tutorial that I personally like watching. So let's get started. If you don't have Python, you should install it, and you want to install the Anaconda distribution from this website, because then you get all the packages and you have all the stuff ready for you. So I would not download it from python.org. You can see the Pandas logo here. I would download the Anaconda distribution. When you've installed Anaconda, you can type conda version in your terminal and you should see something like this. I'm going to be running a Jupyter notebook, so you should download the notebook and run it with me. The notebook is located in this GitHub repository called Awesome Pandas, which I've created. So to clone my tutorial, you copy this, and you want to have Git installed. So again, you check your terminal if you have Git installed. If you're on Windows, you probably don't have Git. If you're on Ubuntu or Mac, you probably have Git. If you don't have Git, you want to go to this website and download Git. Okay? So then go to your desktop and type git clone and copy that URL from the repository. That's going to make a copy of the entire repository in this folder called Awesome Pandas. In the meantime, I'm going to close some of these. Let's close this, close this. There we go. And now I have the folder, so I can go into it. And then I go to the tutorial folder, and you'll see Pandas tutorial part 1 there, part 2 as well. To open a Jupyter notebook, you can type Jupyter notebook in that directory, and it's going to open a new tab where I can from there open the file. So I want you to do these steps so you can follow along with me as I run through this tutorial. Okay, let's get started. So to run a cell, I type Shift Enter. So that runs my first cell, and this runs my second cell. Okay, let's just talk a little bit about Python and Anaconda and the Python ecosystem before we get started. So I've told you this about how to install Anaconda. You can update all your packages using this command conda update all, which you just type into your terminal. I'm going to start a new one. So conda update all, that will upgrade all my packages. And I just did it, so it's probably not gonna be a lot of packages ready for updating. And I can of course type Python to open a shell, and I'll see something like this, Anaconda on Linux, showing that I'm using the Anaconda distribution. Exit will take me back to the terminal. Here is a graph showing the Python ecosystem, and it's from 2013, but still everything seems to hold to this day. So you have Python, it's dynamically typed, and it's some operations are quite slow. So some very clever people made NumPy, which introduces these n-dimensional numerical arrays, which lets you do fast linear algebra, essentially. And then some other people made packages on top of that, and Pandas is in this category. It's built on NumPy, so it uses Python and NumPy, and NumPy allows Pandas to have the speed that it has compared to native Python, which would not be fast for these types of operations. Now, if you've never used NumPy, I really recommend that you try some of these 100 exercises and that you read the archive paper for an introduction to NumPy if you're interested in the details. But doing some exercises, probably smart. I will also talk a little bit about matplotlib, which is a plotting library for Python, which is also very good. And this, of course, is the Jupyter notebook that I'm running right now. And you can get into that too, and you can learn a little bit about how it works and read up on it. I'll talk a little bit about it as I go. Okay, let's import packages. Hopefully everything works. I know that one of these is not going to work, probably. This one, KDEPy, might not work. That's a library that I wrote, and I'm not sure if I have installed it. I haven't, so this is a good time to show you how you install packages. If it's on Conda, you would do conda install KDEPy. And this particular one is not on Conda, so I'm going to have to use pip. It's not going to find this thing. So I do pip install KDEPy instead, and I think I'll just install it on this user. Is that not a flag? Let's see what the flag is. Help, and then I'm just going to grep user. Let's see. Okay. Never mind. I'll just do pip install KDEPy. Never mind that. And very soon this will run. Looks good. Let's run it again, and it runs. Great. So to make it reproducible, I'm going to print out the versions of all my packages that are important here. Let's talk a little bit about these Jupyter notebooks. There are some shortcuts that are really nice to know. There are two modes. One is the mode where you can create cells. For instance, if I'm here and I type B, that's going to create a new cell. And DD twice is going to delete it. I can go up and down. We're using the arrow keys. So I type A for above to create a new cell above, DD to delete, or I can go up here and type B for below and DD to delete. Okay, so B, and if I type enter, it's going to bring me into the cell where I can write some Python code. Shift enter is going to execute and go to the next cell. If I just want to execute this and remain in the same cell, I do control enter. So that's just going to keep me here. I'm going to keep running this like so. What else? If I want to interrupt, if I'm stuck in some infinite loop, I can do II for interrupt. So II, and you can see here it says interrupting kernel, II, and here you see it. And H is very important because that brings up the help. So you can read all about these shortcuts that I don't know, and you can figure it out. But some of these are useful. Enter to go in, escape to go out, DD to delete. That's very useful. You can execute terminal commands using exclamation mark. So I can do ls to list directory contents, for instance, or pvd to see my working directory, print working directory. So this is where I am right now. So that's useful if you want to execute terminal commands. You can use Markdown. To do so, I will type M, and that's going to convert this cell into Markdown. And now I can write like, this is a title, this is a list item, bread, eggs, and so forth. And I will just delete this. You can time cells. I'll show you this. That's useful if you want to compare the running speed of different functions or different approaches. There are some pitfalls when using notebooks, and I will show you one of these pitfalls. Here's one. If I define a variable, I'm just going to give it some strange name like watermelon equals 2, and I execute the cell like so, and then I delete it, it's still there. And by that I mean if I type watermelon, even though I deleted the definition of that variable, it's still, the Python kernel still knows about it. And that's why sometimes it's useful to go to kernel and just do restart and run all, or restart and clear output, because that's going to clear all these variables. So if you're working in a notebook and you create a lot of variables and you prototype a lot of stuff, you might accidentally delete the definition of a variable. And there's also the order of execution. You can define something like watermelon equals 5, and then you can have a dependency above, like watermelon, just printing watermelon, say. Now I can execute this, and I can go up and execute this, and everything is fine. But if I do restart and run all, here it's going to run this before it's defined. So you have to be careful about these things if you really use the notebook. But apart from that, I think it's all good. You can also use LaTeX notebooks, which is great if you want to explain math. So here is some LaTeX, and it looks like it's beautiful. It looks like this. Okay, let's talk about importing data. As I told you, I can run commands using the exclamation mark. For instance, I can run the tree command to see what my directory structure looks like. If you're on Windows, you might not have this command installed already, but don't worry about it. In that case, you can just run ls, or you can run dir if you're on Windows. So ls will list the directory contents. We're going to look at this file in data, in the data folder, and it's called movie metadata, this one. And the head command will print out the first 2 rows of this file. So as you see, you have, this is the first row, and it has information about movies. This is the first actual movie. It's a film, what's it called? Avatar? Is it Avatar? I'm not sure. I think it's Avatar. If you want to learn more about Unix commands, there's this book called The Linux Command Line, which gives a really nice introduction, and there's also a book called Data Science at the Command Line. It's quite useful to know a few commands like head and tree and so forth if you're going to be working with data. Let's import this into Pandas. I'm going to run this cell. I define the columns that I want to import because I'm not interested in all these columns. I'm going to keep it simple by looking at a subset. And the command is pd, which is what I've imported Pandas as, read CSV, and I'm telling Pandas that the separator is a comma here, and I want to use these columns only. This time function is a IPython magic command, and it's going to tell me how much time it took to run this cell. So running this took 21 milliseconds. And it's loaded this DataFrame with 5,000 rows and 6 columns into my memory. Here are the top 2 rows given by the head command, and I can kind of see what it looks like. Yes, the first one was indeed Avatar, and the second one is Pirates of the Caribbean at World's End. And we have the IMDb score and some information about the rating, content rating of the movie. And gross, that's how much the movie made in theaters, I believe. Okay. The shape of a data frame, that's the rows times columns. It's like a matrix, so it's rows times columns always. There are other ways of creating data frames. One is creating them from scratch, and by that I mean that you kind of define the data yourself and you get something like this. If I don't store this in a variable, it will print it out, and it looks like this. It's printed in a clear, nice way here, so you can look at it. If I do, for instance, head of this and just get the first row, it's going to only include max. It looks like this. Okay. I can read HTML tables from the web. For instance, here I define this Wikipedia page. Let's go have a look at it. See what it looks like. It's this, and it has this table of German billionaires, right? So we can read HTML from this URL, and that's going to include all the tables. So it might find several tables here, then it will store them in a list. I only see one, so I think there's just going to be one. But anyway, the return value is always going to be a list. So to get this list of net worth of Germans, we take tables and retrieve the 0 index. So let's run this. And here we have it. Nice. That's this table in Pandas. Cool. Asserts are a cheap way of testing something in Python. You can think of it as a sanity check, or just it's supposed to be a really cheap test that always kind of it's always going to be true. So you wouldn't use this to test something that's computationally expensive, and it's not a substitute for proper software testing, but it's useful for these small sanity checks. For instance, now I'm connecting to a website and I'm downloading data. It might fail for several reasons. The connection might not be there. I might not have internet access. The content of the site might change. Maybe there are several tables and this is no longer the first one. And to guard against silly errors, I add some asserts. So for instance, I assert that the length is greater than 0. That means that I get more than 0 rows back, which seems sensible. The second thing that I assert is that the name column is unique. So no name should be here twice, because these are Germans by net worth, and although it is possible that 2 people with the exact same name both make this list, I think of it as very unlikely, so I'm going to add that test. And we have now stored it as DataFrame net worth, DF net worth. Okay, there is a final approach that's very common, and that's reading from databases, and you can do that using the PyODBC package. And the code would look something like this, and it lets you read code from databases into Pandas. If you work in a company where you have a lot of data in a database, this is great, because you can read from your database directly into Pandas, and all you need is a SQL code, a select statement to retrieve data. I will tell you that if you have a lot of data in your database, you might want to do some reduction of the data in SQL before you load it into Pandas. If you have a desktop computer, you might have 8 or 16 or 4 gigabytes of memory. So you might load so much data that you don't have the memory to actually store everything in memory at once, because when you use Pandas, you have to be able to store everything in memory. What I've imported is a very small file, like 8,000 rows, and that's not a large file. Let's look at it quickly. The file that we loaded is this. It's 1.5 megabytes, so that's a small file. There's no problem fitting this into memory. But if this file was huge, if it was several gigabytes, then I would have to be a bit more careful and maybe a bit more clever about how I analyze it in Pandas, because it is dependent on you fitting everything into memory. So in summary, if you have a lot of data in your database, you might want to do some pre-processing in SQL and think about how much you actually load into memory. But apart from that, it's all good, and typically you don't have to think about this unless you have at least 10 million rows. Up to 10 million works fine on modern computers. Let's talk about mutable and immutable objects in Python. Lists are mutable objects. I can create a list in memory and I can change it in place. For instance, here I create a list of scores and I sort it. This sort function, it does not return a new instance of the list. It actually sorts this list in place, and it will return none, and it will modify the actual object. So when I print it, it's sorted. Strings, on the other hand, they're immutable, which means once you've created them, they can't be changed. So if you call a method such as capitalize, it actually returns a new instance. So the difference is here it modifies the existing object, and here it will return a new object, because strings are immutable. So once created, you can't change them. Pandas DataFrames have the ability to be both, because some methods on Pandas DataFrames, such as methods are things like this, and they will have this parameter in place, yes or no. Do you want to do the operation in place like this, or do you want to return a new instance? And by default, they return new instances, and you should just let them return new instances and think of Pandas DataFrames as being immutable objects. So you have to think about that a little bit. If I take my df and I do head, it will actually return a new object. So if I say temp equals df head, and then I print out temp, that's actually a new data frame with just the 5 top rows of this df data frame. So if I do something like this, sort values, and I sort them by gross, say, then I haven't actually sorted this. I've returned a new data frame that is sorted, but I have to catch it if I want it to persist in the next cell. So I would do something like this. So it's exactly like strings here. They're immutable, so you kind of have to catch them in a new variable, if that makes sense. When you do an operation, you have to catch it if you want it to persist in this on this name. Okay. One thing that's very typical is that you load some data and you're unhappy about the names of columns and the data types. So let's look at this rename function first. I'm not a fan of these names, and maybe I want to change them to something like this. So then you would use the rename method, and you would use columns as input. This will return a new data frame, so I have to catch it, because remember they're immutable, so I have to redefine it, and it will change the names, mapping from these previous names to these new names. I can also send a function which will be applied to every column. For instance, here I send a string capitalize function which will then capitalize these. So first I apply this, and then sorry, that's a different data frame. So on this df with the movie data, I do string capitalize and use this function. I could do like string upper, for instance. It's also a method on strings, or lower, or capitalize, for instance. So that's how you would change names of columns. I recommend having no spaces and just being consistent. So if you use capital letters, everything should be capital, but I prefer this naming convention. Okay, data comes in data types. If you have numbers, they should be represented as numbers. For instance, gross hair being a float, I'm happy about that. IMDb score being a float, I'm happy about that too. And by object here, it could mean any Python object, but it typically means string. So everything here is a string, the director name, and then it will not say string, it will say object. So this looks good to me. Movie title should be strings, and yeah, looks good. This one is a bit tricky because recall that the net worth in this data frame, it contains text, and this is not how you want to encode it, because for instance, if I try to sum these numbers, it's not going to work because it's encoded as a string right now. So I want to change it, and here is how I would do that. I would say that the data frame, this column, net worth numeric now, is equal to net worth, and then I use string replace space billion with nothing. So if I do that, it will look like this. Let's see. Here is the new one. This is the old column, and this is the new one that I've defined. But it's still not a number. It's still a string. And I can check that by doing something like df net worth and then net worth sum dtype. Net worth sum num, sorry, here, and that's still an object. So what I want to do is apply this float function. We're going to talk more about this, which is going to convert everything to a floating point number. And then if I run it, it looks the same, but upon closer inspection, it's now a float. So that's what I wanted. So I have two columns now. One is the one that I can actually operate on, and this is kind of worthless at this point. So I could actually just get rid of this, and I'm going to talk about how to do that later on. Okay, so now I've just kind of given you an introduction how to load data from various sources. I've talked about how to rename the columns and how to change the data type of the columns. And that's important, and you should do that when you load new data into Pandas. Just make sure this is all good, and it'll save you a lot of time further down the road. Let's talk a little bit about getting help. When I look at functions, you might wonder, what's the signature? What parameters does this function take in? How can I read more about this function? There are several ways to do it. For instance, if I do something like df and I do start typing sum or just s, and I get all these method names that I can call, I can do su and then shift tab, sorry, sum and then shift tab, and it will give me the signature of the function. If I expand using this cross, it will allow me to scroll down, and I can read about all the arguments that the sum method takes. So that's one way of getting help. Another way is just using a question mark like so, and this is a feature of notebooks. If I execute it, I get the same help text here. I can look at examples. I can close it by clicking here. This question mark can also go in front, I believe. Yeah, works. And the final thing that I can do is call Python's built-in help, which will also give me the same text. This is also available on the web, so I can do DataFrame pandas sum, and it will probably give me the official documentation here, and this is the same thing that we just looked at. So this is the rendering of that string, and here it looks a bit more pretty, and you can read about what it does, and you can look at these examples. So there are many ways to get help. Let's talk about summarizing data. To look at the data, we can call the head function. N controls how many of the top rows you actually print out or return from this method. One thing that you can do instead is to sample 2 random rows. This might be better because in some instances you have time data, so the first rows are always from the first time, the first point in time, and you might just want a sample where you look at where you have higher probability of seeing all sorts of things. So then you would do df sample, and you might change this to 10, for instance. Just look at 10 rows, and this can tell you a lot about the data. You see here that there are some missing values for director names, and you see missing value here, and well, none of these are missing, but that's just 10 values. They might be missing. And you can call this again and again, and you can inspect the data like so. This random state is important if you want to have something that's reproducible. If I do something like this, it's still a random selection, but it's reproducible. So if I run it again and again, it just returns the same rows. A new number here, a new seed, will give me something different, but it's still reproducible. So that's important. I like to sample just to get a look at the data. After looking at the data types, we want to look at null values. Another way of getting some information is to use the info command. That's going to give me information about all the columns. It's going to tell me how many that are non-null, so they're not missing. And it's going to tell me the memory usage, the number of columns, the range, and so forth. So you can inspect this and look at the data that way. So for instance, here I see, including 0, so 0 to 5042, so it must be 5043. So there are actually no missing IMDb scores. They're all non-null, while there are quite a few missing gross values. So almost 1,000 of those are missing. Here's another way to count missing values. I can use DataFrame is null. And that's going to give me a new DataFrame with every index telling me whether it's missing or not. So it looks like this, and this particular thing is missing. This is missing, while in this row nothing is missing. So then I will call sum on that. It's going to sum over the rows, and it will look like this. So I sum over the 0th axis, and that tells me how many are missing in each column. So I can then divide by the length, which is the number of rows, and it will give me a percentage of how much is missing. So I can immediately see now that 17% of the gross values are missing, while 0% of movie titles are missing and IMDb scores. Okay. If I run this again and I look at the type, this is a Python built-in telling me what the type of object it is. It tells me that it's a series. And you see this here, that it doesn't print like a data frame, because if I convert it to a data frame to DataFrame, it will print more, isn't it, to as DataFrame. Okay, let's debug this. I think it's as. I think I type it 2frame. Okay, let's copy this. If I do 2frame, then it will look prettier. So this is a data frame and this is a series. What's the difference? A series is like a vector. It's a vector with a name and an index basically, and a lot of methods that Pandas defines. While a matrix, you can think of a matrix in many ways, but one way of thinking of a matrix is that it's a collection of columns. And likewise, the Pandas data frame is it's a collection of series. So if I wanted to make this prettier, for instance, I could take these null values that I've printed out here, and it doesn't look as pretty because it's a series and it doesn't really include the same, it's just this vector, labeled vector, you can think of it as. So if I want to make it pretty, I could do something like this. I could convert it to a data frame, like so, and now I'm doing it just so that it'll print prettier. But I could also add more columns now, which I can't do to a series because a series is just a single column. Then I can compute the transpose using .t. So that now it's definitely a data frame because it has several columns. And then I can rename this index, this 0th index, to missing values, and then it looks pretty decent. So it gives me the number of missing values for everything. And this is a trick that I've been using. It's called method chaining. And it's due to the fact that these objects are immutable, and calling a method will return a new instance of the object. So I can chain these methods, and you can write it like this if you want to. And I think this is a great way to write Pandas code, and it's pretty readable and it's extremely concise. So one advantage of writing your code like this is you don't have to redefine your variable df all the time, and you can do one line of code per method, which is very readable. So you can document it like this. And if you, for some reason, don't want to do some operations, you can just uncomment those lines. So you can do something like this, and I can, if I want to figure out what this does, sometimes the best way to figure out is just to uncomment line by line. So I have my data set, I compute if every entry is missing or not, like so. Then I sum over the first axis, it looks like this. It returns a series by default, so I convert it to a frame, prints differently. I transpose it, and then I rename that first row. And that's really concise code. And if you have advanced operations and you do a lot of aggregations and stuff like that, it looks really dense. It's almost too dense sometimes. So you kind of have to uncomment, and that's the best way to figure out what's going on. If I read my own code that I've written a long time ago, I might forget, so then I just do this uncommenting trick and I think about it as I go. So that's method chaining. There are a lot of other functions for summarizing data. For instance, these, you can do counts, number of unique, mean values, standard deviations, minimum, maximum, quantiles, and so forth. There are a lot of methods defined on DataFrames. We can list these using the dir command. That's a built-in Python command, and it says returns the names in the current scope. So which methods exist on a data frame? Just run this. It gives you everything, and it is a long list. These are all the methods available to us. Let's count how many there are. Let's do length of that list, like so. That's 460 methods. Some of these contain underscores, so they're not meant to be called by us, such as these and these. So let's list everything that doesn't contain an underscore in the first character. So I would do something like m method for method in, if method 0 is not equal to underscore. So that's the API that they want us to call. And there are many methods here. Let's count how many there are. Specifically, I do the length of that list. So there are 223 methods. And some people say that this is too many. It's too hard to keep count. And I kind of agree. It's a bit much, but typically you don't use everything. There's this API reference that's really good for Pandas, where you can look at in detail. Like, click at general functions, and you get all the general functions here. So I think, can we look at everything? No, DataFrames. And then you can just look at what's available, and typically if I go into one of these, like group by, I will get the doc string and I might get some examples. So here are some examples too, so it's really easy to get started and just looking at this. If you want to learn something new, you can just browse this, and I'm sure you can learn about methods which you don't know about. Let's look at a few more ways to summarize data. I can describe the data using this describe function. Now I've added some additional parameters. I want to compute the median, the percentile at 50%, and I want to include everything. And this fills the missing values because, for instance, the mean value of a string column is not defined, so it just returns not a number, and I fill these not a number entries with just an empty character, so it looks like this, just to make it prettier. This is also something that you do typically when you get new data. There's the shape, which I've already showed you. It's the rows times columns. I can drop missing rows, so this will drop every row that has any missing value, and you can see that the shape goes from 5,000 rows to 4,000 rows after dropping these. And if I just uncomment this, you will see what it looks like. Nothing here should be missing at all. I can use this to actually let's see, what does it do? Drop duplicates. Yes, there are some duplicate columns, duplicate rows here, which I might want to get rid of in an analysis setting, depending a little bit on the data set. But that's also a very useful method to know about. I'm actually going to perform these two operations now. I'm going to drop all the missing all the rows having any missing values, and I'm going to drop all the duplicates, and this will return a data set that's more clean. So of course you would be careful about doing this in a real setting. You would inspect what the missing values actually represent, and you would think long and hard about what to do with those values. But this is a tutorial, so I'm just going to drop everything. Okay, let's talk about unique values, value counts, and sorting. I can access a column in two ways. One of them is just do dot and then write the name. This is why I don't want spacing in my names, because then this would not work. But if I have underscores, it works, and I can do this. And this gives me the unique values in this particular column. It's not the same as asking whether that column is unique. It's not a unique column because there are duplicates, but this will actually give me the unique values. I could also access this in a slightly different way. I could do this, and it gives me the exact same answer. There are two ways to access columns or access a single column in Pandas. Both of these work. They have some advantages and disadvantages. The advantage of this thing is that if I do df cont, I can use tab. So I can write cont and then tab to autocomplete. So that's fascinating. Unique didn't autocomplete. Okay, whatever. That's probably because it doesn't know what this is. But if I now, no, it doesn't work. Okay, well, it autocompletes this, and it's less typing. Disadvantage is that if you have something called sum, if you have a column named sum is already a method on your data frame, so it's going to get confused. It's going to say it's a bound method, which is true. Sum is a method, so if you take any of these 223 names that are actually in the namespace and you use one of those as your column name, Pandas is going to refuse to return the actual column. It's going to return the bound method instead. So I prefer this one, but just because it's faster, but in a way this is more consistent with the rest of the Python language. And some people are not happy about there being two ways of doing it, but I don't think it's a problem if you know about it. I can drop duplicates and convert to a list. That's also going to do the same thing, because I take this column, I drop all the duplicates, so then I'm left with the unique values, and I can, for instance, convert it to a Python list. So here's a list of all those content ratings. I can do value counts. This will give me each value and count the number of occurrences. Notice again that it returns a series, and if I for some reason want it to be a data frame, I can call toFrame and it will return a data frame instead. This is how you would select several columns. We're going to talk more about this later, but using this I will first select two columns, the movie title and the gross, and then I will get the three largest values by gross. The three movies with the largest gross value, I should say. Here's a little bit about sorting, which we're also going to talk more about later. I can sort by country and then IMDb score, ascending and descending, and I can put all my missing values last. And this head will just make sure that I return the top 5. If I don't do it, I will get the entire, or not the entire thing, but a lot of it. It's the middle is truncated, as you see here. So this tells me that in Argentina, the movie that has the highest rating is this Secret in Their Eyes. Okay, let's talk about basic visualizations. We're also going to talk more about this later. I just want to show you an example. You might want to look at correlations. You can do that like so. By default, it will just include numerical values, and this will give you the Pearson correlation coefficient. That's not really related to visualization. It's just, but it's about aggregating your data set and kind of understanding it. So I think that's why I put it here. Let's talk about actually visualizing stuff. Here's a graph. I first take the content rating, I compute the value counts, and then I convert it to a data frame. And then I call the plot method and then the horizontal bar. And this is the signature of that function. And if I just remove all of this, it looks a bit more clean. And I can change these defaults. So for instance here, I changed the figure size to 10 by 5. So it looks like this, but I could have set it to 5.5 or 5.3 to get something smaller. And as you see, there are a lot of options here. For instance, I could change the title really quickly and say my, let's call it counts of content rating. Then I get this. So that's how you can visualize data. I can do a kernel density estimate of the IMDb score, which shows me the distribution of the score. Sorry, there's an error. You see, I'm actually computing the kernel density estimate of the gross, but the title says IMDb score. So let's fix that. It should say distribution of gross value. Okay, I can turn on or off this grid. This parameter tells me the bandwidth of the kernel density estimate. If I change this to 100, it's going to look more wide, or 10 even, 1. And if I make it really small, then it's going to be more jagged. High, you would say that this is high variance. And here's one for line width as well. So you can play around with this, and it has nice plotting capabilities. Here's the final one. Scatter matrix of 2 columns shows you the distribution of gross, the distribution of IMDb score, and then scatter plots of these two against each other. So this can really help you visualize your data if you have numerical data, and really examine. So you see, for instance, here IMDb score, most are between 5 and 8. And it seems to be the case that can you interpret this? I should be really careful about making an interpretation, but it might seem like the higher the score, the higher the gross. Somehow that you don't have a lot of movies with low score having high gross. They would be here, but you see movies having high IMDb scores having also high gross values. Let's talk about selecting and computing new columns. You might want to filter out a few columns, a subset of columns or a subset of rows, and this is how you would do it. A data frame has an index. Here it's just numbers. Recall that df looks like this. So this is the index 0, 1, 2, 3, 4, 5, and so forth. Do you see that 4 is missing? That's because we dropped rows with missing values. So I'm guessing that column 4 was a column which had a missing value, and we removed that one. So now we have an index which is not, it skips over some values there. We could fix that if we wanted to, but we're not going to really focus on that right now. But it has an index, you can access it like so. It has columns, and these can be accessed like so. There's this very useful method called toNumPy, which will return the underlay. toNumPy. Is it just value then? Values. I thought they introduced a new method called toNumPy, but maybe I don't have the newest version of Pandas. Pandas toNumPy. As matrix toNumPy array. Okay, we'll just use values for now. I believe they introduced one called toNumPy. Use DataFrame values. We recommend using DataFrame toNumPy instead. And this was introduced in version 24. Let's look at our version. Scroll up, and we see that our version is 23. Okay, so that's why I don't have it. I will shamefully use values instead while demonstrating this. But you should use toNumPy if you have the newest version of Pandas. This returns the underlying NumPy array with all the data. And this is very useful if you want to pass your data to another library which does not expect a Pandas data frame as input. And you can use this and you can get the underlying array. So if I do type, this is a NumPy n-dimensional array. But if I do type of df, then it's a data frame. So you can just access all those values. And of course this is not going to work, so I change it to .values, and here is the gross column. I drop all the missing values. I don't think there are any anyway, but then I get the values. So that's the vector of values. Okay, to select a subset of columns, recall that these are the columns. I could select a single column using this syntax, or I could use the slightly more Pythonic syntax like this. I say that it's Pythonic because it looks like accessing dictionaries in pure Python. If I want to select 2 or more columns, I can use this syntax. It's pretty convenient and it lets me access several columns at once. There are some more general functions, or methods I should say, on this data frame that you should know about. One of them is location, LOC. The other one is iloc for index location, which I'm going to show afterwards. This one lets you select a subset of rows and columns in one go. So this means every single row and these 2 columns. And notice that it's not a function, it's an accessor, so it's a square bracket here. Using this lock, it's not a method. So this says give me every row and these 2 columns, and then I do head. So instead of doing head, I could do something like this. Give me the first 2. Yes, up to 2 here. So that's apparently that's inclusive. Okay. 4, 5. How does this work? If I do 1. Okay, so it's based on the actual number here. Yeah, it's based on the number. So if I do 1, it's going to give me up to 1 inclusive. It looks like 0, 1. What if I do 2, 3, and then 4? Yeah, based on the numbers, doesn't give me a new one. You see that? 3 and 4 gives me the exact same because 4 doesn't exist. But if I do 5, it gives me a new one. Okay, fair enough. Notice that if I don't put this in a list, it will return a series. It will give me this single column or series back as a series object. But if I do this, it will return a data frame. So different behavior, and you might want to be aware of it. I can drop columns instead of selecting columns. If I want to do that, I would use the drop method, and I can specify the columns like so. So here I drop these columns from the dataset, and I'm left with these columns afterwards. Here's iloc, which I talked about. It's in the integer location based indexing. So this says give me columns 0, 1, and 2 from the dataset, and give me rows 1 through 3. And that's based on not these numbers, but simply the location in the dataset, in the data frame. So this is just, yeah, it's integer location based indexing. So I rarely use this because I find it more convenient to work with the names rather than the integer locations of things. But you should be aware that it exists, and in some cases it's really useful. Okay, selecting subset of rows, you've already seen head. Not gonna talk about it. You can do something like this to access a subset of rows. So here is row 0, 3, and 6, and every single column. I can do something like this. So it's smart enough to realize that I'm looking for rows here, not the columns. Here is a little bit of filtering. If I want to do some filtering on the rows, I can do it like this. I can say df, where df country, that column, is not equal to the USA. So this will actually return a vector with true and false entries. And using these true and false entries, I can index the rows of this data frame. So it looks like this. And now it returns every row which is true in that vector which I computed. And then I get the 3 largest by IMDb score. So these are the 3 largest movies by IMDb score, which are not made, I guess, in the US, or at least this country column is not equal to the US. I can do more advanced stuff. I can create this Boolean mask where I say DF country is not equal to the USA and the content rating is equal to PG-13. And these are the 3 largest movies by IMDb scores satisfying these 2 criteria. You have to use parentheses here. That's important. So this computes a Boolean vector, this computes a Boolean vector, and this is element-wise AND of these 2 vectors. And you can print this out and look at it if you want to. But if I remove this, it's going to get very confused because it won't know how to compute it, since it will not compute this first and then use the operator finally. Instead, it might, I think it will use this operator first and it will try to use this operator on these, which will fail, and then everything just fails. So you have to do this to tell Python what the correct way to evaluate this, the correct order to evaluate this expression is. It's like addition and multiplication. You always do multiplication first if nothing else is specified. In this case, you have to specify to do these operations, equality checks, before you do the AND, the element-wise AND operation. And will not work here because it's not element-wise. You have to do this element-wise AND. Okay, selecting subsets of rows and columns at the same time. We've already seen this, but I just wanted to show a few more examples. Here I can, for instance, say that I want the rows in which the IMDb score is greater than the mean. So these are above average. And I might want to select the rows where the movie title contains the word ring, or the characters ring. And here you have those movies. So these are movies that are above average in which the movie title contains ring, for instance, Conjuring here. Okay. If I want to do some more dynamic processing of columns, I could do something like this. I could first define a list in Python where I say C for C in columns if underscore is in C. So this returns every column that has an underscore. And then I could get those columns from the data frame. That could be very useful if you don't want to specify a long list, but there is something in the column name, for instance, that you're after, that you're looking for. You can do this a bit more dynamically than actually typing everything out. Here's a more advanced example. I'm just going to show you what it returns first. It returns only the numerical columns. And I do this dynamically. I say that the numeric columns, that's equal to this. Let's print it out. So I say df, where did I say data types? Okay, data types, that's this. You've seen this before. This returns the data type of every column and it returns it as a series. So then I index this saying I want the rows where the data types is a float. So that will return these two. Then I retrieve the index of that series, which will give me the names like so. And then I convert this to a Python list like so. And then I get those columns from the data frame like this. So then I can get all the columns having numerical data dynamically. I can create new columns. This is the last thing we're going to talk about in this tutorial, and then in the next tutorial we're going to get into more detail and talk about more stuff in Pandas, but computing new columns is important. Here's how you make a copy. I'm just going to make a copy of the entire data frame because I'm going to play around with it. I could, for instance, decide that I want to compute a logarithm of the gross column. So here's one way of making a new column. I simply say that on this temp data frame, this temporary data frame, the log gross is equal to the gross column. And then I apply this logarithm base 10 function from NumPy on this. So that gives me this new column here, log gross, with this computation. So that's one way of doing it. Now I can, for instance, investigate the relationship between the log gross and the IMDb score. And I would say that I see a slight pattern here. It seems like the higher your IMDb score, the higher your log gross. Seems to be a pattern. We're not going to speculate too much on this, but I would say it looks like we might be onto something here. Let's look at something a bit more advanced, how to compute stuff. I will show you the output first, and then I'm going to backtrack and I'm going to show you what this actually does. I'm going to do that the way that I do it. I uncomment and look at what I meant to do here. So I do something like this. Okay, so first, what's temp? That's just the entire data set. And then what I wanted to show you here is this assign method. And it works, this does exactly what I just did. It's the same thing as this line of code, but here I have to actually compute it, and then I have to define it using equality. So I can't really do this using method chaining. I can't do this as part of method chaining. So here's a better way of doing it, because I can keep doing method chaining afterwards. But essentially you use assign, and then your input parameter, that's going to be the name of the new column, and then you have to give it a function. Here I use a lambda function because I don't want to define a new function using def. It takes in the entire data frame, and then it retrieves the gross column and it applies the column. So it says that this new column is the result of this computation, which must be in a function here. Then I apply a filter where I just choose a subset of the columns. I do a group by. I'm going to talk more about this later. I'm going to, by country and content rating, I'm going to get the mean log gross. So now it looks like this. So the average log gross for PG-13 Australian movies is this, 7.3. Then I will reset the index. I'm going to talk more about this later as well. Now it looks like this. Then I sort the values by country and log gross. So we have first country and then log gross. I set the index. Why did I do all this? I think I did it just to sort. I don't actually remember now. And then I'm going to assign log gross equal to itself, but I'm just going to round it to 2 decimal places. And here I have this data set telling me for every country and every content what's the average log gross in with 2 decimals of precision. And here's the head of that. I don't remember why I did reset index and then sort. Is it sorted already? Let me check. It's already sorted, so that might have been unnecessary. G, A, B, C, D, R, U. Yeah, I'm not sure why I decided to do that. Okay, well, at least you get to see an example of what method chaining looks like in action. Okay, final section is applying functions. There are many ways to apply these functions to series and data frames. and you should just kind of know about the difference. There's map. It maps an element-wise function, such as string or float, which takes a single object and returns a single object. Apply can apply a vectorized function, such as numpy's log and sine functions. Aggregate applies an aggregation function. By that I mean a function taking an n-dimensional array and returning a single number. Examples include the mean, minimum, maximum, standard deviation, median, and so forth. And then on a data frame, it's the naming convention is slightly different. Here it's called apply map instead of map, the one that works on every single element. But apply works pretty much the same, and aggregate is the same thing. So let's look at it. This will map a function onto every single element of the gross column. So I map float. I could do something like this if I wanted to, lambda x times x. So that would square every value, or I could do something like np log of x. And it's an element-wise operation. Or I could do int, like so. Dictionaries are also maps. But if I don't have the correct key, then it's going to map to not a number. For instance, I could map PG13 to the string inappropriate for children under 13. And PG to the string may not be suitable for children. But if I have something like this, if I have a content rating which is not among these, it will just map to not a number. So I have to make sure that I specify all my keys if I want to use a dictionary here as a map. The apply function can apply a numpy vectorized function. And this is faster because you can leverage numpy. So I could do this with map as before, but if I do apply and I use this vectorized function, it will apply it on the vector and it's faster. Let me just show you that. If I do from math import log as Python log, so that's the built-in logarithm from Python, and then I do time it, and I use apply, and I apply this function to every single element in turn. That's going to take more time than using this vectorized function. The result, of course, if I just take a logarithm, it's going to be the same. Just ignoring the base. If I do something like this, that's going to be faster. Sorry, this should be map. Okay, let's see. So this one will iterate over every single element and compute it element-wise, not knowing that it's a vector and that it could be vectorized by numpy. And this apply is going to use the numpy universal function, so it's going to be faster. And here you see the speed difference. This is faster than this because this loops in Python and this operates on a vector. So that's the difference in the case of series between map and apply. So if you have a vectorized function that you can use from numpy, I would use apply. If you have to do it element wise, you can still use map. And in this case, it doesn't matter much because we only have 5,000 or 4,000 rows. But if you have a lot of data, this can matter, and you should use apply if you can. Okay, I'm going to delete these. The final thing is aggregation functions. If I want to compute the mean of the gross, column, I could do something like this. I can aggregate, and then I can aggregate by this function. There's also built-in support for the common one, so I could do this, and it's going to return the same thing. But this is more general, since it can take in any function which aggregates. For instance, I can define my aggregation array and do return NP standard deviation divided by NP mean, and I'll just copy this like so. And now I've defined this is, I think it's called the coefficient of variation, standard deviation divided by mean. Let's call it that, coefficient of variation. I think that's the name for it. And I can do this. And sorry, the mean returns a number, standard deviation returns a number. Why does it return? Why does it not aggregate for me? Array, okay, let's print array, see what it is. It's just giving me all these numbers. That's strange. df gross aggregate. Okay, let me just try with mean and see what happens. Okay, this works differently. That's a bit strange. Can't really tell what's going on here. I'm really just redefining the mean function. Huh. Okay, I'll have to think about this a little bit. I'm going to give you an example on a data frame where I know that this will work. But this is a bit strange. Okay, I'll show you how I can compute it. What I would do if I wanted to do a computation like this is I would call this function and I would simply call it on the values. So I would do something like this, and then let's again add the standard deviation. So it looks like this, and this is how you could compute such an aggregation function over a single column in a data frame. I'm not sure why it didn't work. Functions on data frames. Okay, it's same thing basically. Apply. You can apply it to a function to several columns. So now it will take the logarithm of each of these columns, and it will do so in a vectorized fashion. Apply map. It's going to work element-wise on every single one of these. For instance, converting everything to an int. There are some built-ins, such as the mean, some aggregations, and this will aggregate the mean for every column. So it looks like this, and here's what I wanted to show you. You can specify your own aggregation function, such as this, and then you can do this on a data frame. So if I remove this, will it work? Yes. Okay, so I think aggregate, it might have different behavior on data frames and on series. Yes. So if I apply aggregate to this, which is a series, then it gives a different result than if I apply it to a data frame, which looks like this. So we kind of figured out what's going on. There's something about the aggregate and how it works on series and data frames. So you want to use it on data frames to have the behavior that I'm sketching here. Okay, thanks a lot for watching this. I hope I didn't go through too much in too little time. In the next video, we're going to talk about filtering and sorting, the split apply combine pattern, plotting, time series, and machine learning. So please watch the next one if you're interested in any of that. Thank you.